Worked example 8.
So I'm going to go ahead and sketch the circuit here. Pretty straightforward. Two resistors connected in parallel. Now, if you sketch it in a slightly different orientation, for example like this, that is also absolutely fine, doesn't really matter. And we're told it's 20 ohms, so we'll call that R1, R2, 20 ohms and 40 ohms. We've got a 12 volts battery. Part B, determine the total circuit resistance. So for part B, RT is what we're after. And the equation that we use in the book here is 1 over RT is 1 over R1 plus 1 over R2. 1 over RT equals 1 over 20 ohms plus 1 over 40. And when we put just this into the calculator and hit equals, we end up getting 3 over 40. Now, of course, that is not the final answer. That's not what we're looking for. We're trying to get RT, which is currently stuck underneath here. So the easiest way to do that is to actually flip both sides. So we end up with RT over 1, which just becomes RT, equals 40 over 3, which becomes 13.33 ohms of resistance. So our total resistance for the two resistors in parallel here has actually dropped to 13.33. And just a little reminder, as you add more resistors in parallel, the resistance will always get less. It will always decrease. In fact, it will always be less than the lowest value of resistance in the parallel section. Part C, it asks us to determine the current flowing through each branch. So when we talk about branches, we're basically talking about each of these sections here. So that's one branch, that's another branch. So it's wanting us to figure out I1 and it wants us to figure out I2. There's a couple of ways we can do this, but the easiest way in my opinion is to recognize that the voltage supplied is going to be the same voltage over R1 and the voltage over R2. We can say that Vs equals V1 equals V2, and so I1 is going to be V1 over R1, which in this case is going to be 12 divided by my resistance R1 of 20. That's going to equal 0.6 amps. I2 is going to be V2 over R2. In this case is going to be 12 over 40, which is 0.3 amps. In part D here, we're asked to work out the power of each resistor. So power 1 is going to be I1 V1, which is going to be equal to our I1 of 0.6 times our voltage V1 of 12 volts. And that gives us 7.2 watts of power. And P2 will be I2 times V2, which is 0.3 times 12, which is 3.6 watts of power. For part E here, we are asked to calculate energy consumed by each resistor. So E1 is going to be P1 times our T1, and in this case that is 4 times 60, so which is going to be 7.2 watts times 4 times 60, and that is going to give us a total of 1.7 kilojoules of energy. E2 is going to be P2 times the same amount of time, so in this case 3.6 times 4 times 60, which equals 860 joules, or 0.86 kilojoules of energy consumed. Question 2. 3 resistors, 2 kilo ohms, 1.5 and 3 kilo ohms are connected in parallel to a 24 volt battery. 24 volts and 2 kilo ohms, 1.5 and 3 kilo ohms. To first of all calculate the total circuit resistance, RT. So 1 over RT is 1 over R1, R1, R2, R3, plus 1 over R2, plus 1 over R3. So I'm going to substitute my values in, leaving them in kilo ohms for now, and plug that into the calculator, and what I end up getting out is getting 9 over 6. But of course we've got 1 over RT equals 9 over 6. So what I need to do is flip both sides to invert, and that will give me RT is 6 over 9, which equals 0.67 kilo ohms, or converted into regular ohms, 670 ohms of resistance. So my total circuit resistance is 670 ohms of resistance there. Part B asks us to determine the current flowing through each branch, I1, I2 and I3. So in this case we've got the voltage over each resistor because it's in parallel, so we know V1, 2 and 3 is 24 volts, and we also know the resistance of R1, 2 and 3, so we can work out individually the current through each based on that. So I1 is going to be V1 over R1, in this case 24, divided by 2000, and that gives us 12 milliamps. I2 is going to be V2 over R2, and V1 and V2 are the same, so that's 24 over 1500 ohms, which equals 16 milliamps. And lastly, I3 is going to be V3 over R3, which is again 24, this time divided by 3000, which equals 8 milliamps. So our three individual currents are 12, 16 and 8 milliamps through each of the branches. Part C, determine the total power of the circuit. Well, our total power is going to be equal to P equals IV, or it could be equal to I squared R, either way. I'm going to use the top one because we have the voltage and we can work out our supply current by adding the three together. So IS is going to be equal to I1 plus I2 plus I3. So that will give us our supply current. So that's 12 plus 16 plus 8. Well, that gives us 36 milliamps. P times Vs. So in this case, 36 times 10 to the minus 3 multiplied by our supply voltage of 24 volts, and that gives us a total of 864 milliwatts. Part D, we're asked to calculate total energy consumed by the circuit after 12 hours of running. So energy is what we're looking for. Power we just worked out was 864 milliwatts, and the time is 12 hours, which converts into 12 times 60 times 60, and that gives us energy total is going to be 864 times 10 to the minus 3 multiplied by 12 times 60 times 60, and that gives us a grand total of 37 kilojoules of energy. Question 3. Three resistors are connected in parallel to a 24 volt battery with branch currents of 0.5 amps, 0.75 and 0.9 amps respectively. Determine each of the following: the total supply current, the resistance of each branch, the total circuit resistance, and finally the power of each resistor. So in our parallel circuit here, first question is to work out the supply current, IA, or IS, sorry, for part A. So in a parallel circuit like this, our supply current splits down each of the branches. So in this case, IS is going to be equal to I1 plus I2 plus I3, which in this case is 0.5 plus 0.75 plus 0.9, and that gives us a total of 2.15 amps for our supply current. For part B, we're asked to work out resistances 1, 2 and 3. So in this case, we're going to be using the fact that we've got our voltage 24 over each resistance, and we've got the current here for each. So we're going to use Ohm's law, where resistance is equal to V over I, and in each case it's going to be V1, I1, V2, I2. So V1 over I1 is going to be 24 over 0.5, which is going to give us 48 ohms. R2 is going to be V2 over I2. So that's going to become 24 over 0.75, which is 32 ohms. And then R3, which is V3 over I3, is going to be 24 over 0.9 amps, which is equal to 26.67 ohms. In part C, we are asked to determine the total resistance of the circuit. And there's a couple ways we can do this. I think the easiest way is to use Ohm's law, where we say that RT is equal to the supply voltage over the supply current. Now notice the difference between what we did in C, part B and C here, was that in part B we were using the voltage, the supply voltage over the individual currents in each branch, flowing through each branch, whereas in part C here we're going to be using the total supply current that we worked out earlier. So this becomes 24 volts divided by our supply current of 2.15, and that ends up giving us 11.16 ohms. Now, don't be confused by the fact that that total resistance is lower than the individuals, because remember, in a parallel circuit, the total resistance must always be lower than the smallest resistance in that circuit. Part D is asking us to work out the power of each resistor. So power 1 equals I1 V1. So I1 is 0.5 amps multiplied by the voltage over it of 24, which in this case gives us 12 watts. Power 2 is I2 V2, which is 0.75 times 24, which gives us 18 watts. And finally, power 3 is I3 V3, which is 0.9 times 24, which gives us 21.6 watts of power.